Okay, yeah. So the talk is going to be about, as the title suggests, what is a formal proof? So, like, what is this sort of the very idea of a formal proof? So we sort of are very familiar with formal proofs in different particular proof systems, but this is the sort of, stepping back a level to the question of what is, what do these things have in common that makes us regard them all as formal proof systems? And so I'm going to start with a sort of what I think is a sort of core conception of formal proof. And then I'm going to sort of substantiate the claim that this is a core conception by sort of showing its origins and how it's kind of embedded in the literature. And then the bulk of the talk is going to consider a kind of proposal to add something to that core conception. And then I'm going to go through a bunch of arguments for why we might want to make that addition. And I'm going to argue that none of them are any good. So the ultimate conclusion will be we should just stay with this core conception and not add this other thing that's been more recently proposed. Okay, so to set out the core conception, the first thing to note is that a formal proof is always a formal proof, of some claim. For example, the claim that some formula is a tautology, or the claim that some argument is valid or whatever. And it's always a formal proof, in a particular proof system. So something that's a formal proof in one system will not be a formal proof in another system, and so on. So, okay, so the big question then is, what is a proof system? And I think there's, according to this core, what I'm calling the core conception, there's two essential features of a proof system. And so the first one is a specification of the symbols that are allowed to appear in proofs and of the format of proofs in the system. So the symbols that are allowed to appear and the kinds of ways in which they're allowed to be arranged. And so I will then call sort of any arrangement of the allowable kind of the allowable symbols for that system a proof candidate of that system. And then the second part of a proof system is a decision procedure that takes as an input one of these proof candidates and some claim. For example, the claim that a certain formula is a tautology, or the claim that an argument is valid, or whatever. So it takes as input a proof candidate and a claim, and then it gives you back, yes, this is in fact a proof of that claim, or no, it isn't. So it's the second bit there that's really the core thing that's really doing all the work. And because we're talking about a decision procedure, we have to sort of define what its inputs are. That's one, to sort of define what the inputs to this procedure are. But really the core of this thing is two, this decision procedure for checking whether or not something is a proof of some claim. Okay, and this is not a proof building procedure or a proof search procedure or a procedure for constructing proofs or anything like that. It's some proof systems that we know have such procedures and others do not. But that's not what I'm talking about here. I'm talking about given a proof candidate, wherever it came from, this is a procedure that checks it, whether or not it's a proof of some claim. Okay, so, and then a formal proof, of some claim P in some proof system S is going to be a proof candidate that the decision procedure ticks off, says, yes, this is a proof of P. That's what a formal proof is. So, as foreshadowed, it's always a proof of something, in some system. Okay, so that's what I'm calling the core conception of formal proof. And so what I want to do now is just sort of explain or substantiate really the label core conception by talking a little bit about where this came from and how central it is to the normal understanding of a formal proof. So, well, for a start, it's this idea that, of an effective proof checking procedure as sort of core to the idea of a formal proof system. It's found in various, contemporary logic textbooks, such as the one of mine that Guia mentioned at the beginning, and various other ones that I've listed there. But it's also kind of deeply, it's not just some sort of recent thing that people have come up with, it's really deeply embedded in the origins and sort of central results of formal logic as we know it. So, one place, sort of really arguably the origin of this, is Frege. So this is a quote from the Begriffsschrift. So he says, Frege says, to prevent anything intuitive from penetrating here unnoticed, I had to bend every effort to keep the chain of inferences free of gaps. In attempting to comply with this requirement in the strictest possible way, I found the inadequacy of language to be an obstacle. No matter how unwieldy the expressions I was ready to accept, I was less and less able, as the relations became more and more complex, to attain the precision that my purpose required. This deficiency led me to the idea of the present ideography. Its first purpose, therefore, is to provide us with the most reliable tests of the validity of a chain of inferences, and to point out every presupposition that tries to sneak in unnoticed so that its origin can be investigated. Okay, and then in the Grundgesetze, he still has this basic idea. So this is a quote from the Grundgesetze. He says, the gaplessness of the chains of inferences contrives to bring to light each axiom, each presupposition, hypothesis, or whatever one may want to call that on which a proof rests. And thus we gain a basis for an assessment of the epistemological nature of the proven law. Although it has already been announced many times that arithmetic is merely logic further developed, still this remains disputable as long as there occur transitions in the proofs which do not conform to acknowledged logical laws, but rather seem to rest on intuitive knowledge. Only when these transitions are analysed into simple logical steps can one be convinced that nothing but logic forms the basis. Okay, so the motivation here is ultimately epistemological. And the idea is to present a proof in a way that such that all the sort of substantive things like the rules of inference that you're applying and the axioms that you're relying on, they're all stated, well, they're all sort of represented explicitly, well, not the rules of inference, but it's all there in the proof so that when it then comes to checking the proof, it has just ended up becoming a kind of mechanical procedure. So the thought is something like, if when you were going through the proof, you had to sort of think, oh, hang on, does this step really follow from that one? And then you're like, oh, yeah, it does. Like you're using some sort of intuition or insight or something like that. Then that's the sort of thing Frege wants to avoid, where every sort of substantive thing that goes into establishing the theorem is meant to be, rendered as an axiom or a rule of inference, so that once you've rendered the thing in that way, then checking through it, the sort of upshot of that is that checking through it just becomes this kind of simple mechanical procedure. So hence the idea. I mean, Frege was a bit before the idea of, effective, the definition of an effective procedure and so on, but the basic idea is there that the sort of upshot of his motivation for formalizing proofs in this way is going to be that when it comes to checking them, it's just this simple mechanical procedure. Okay, so that's sort of one origin of this idea, that it's essential to formal proof that once the proof candidate is there, the procedure of checking it is just a purely mechanical exercise. Okay, another origin of the idea is Hilbert. So this is a passage about Hilbert. Couldn't really find one kind of passage in which Hilbert says all this stuff in a really snappy way. So here's someone else talking about him. For Hilbert's axioms for various geometries, he had proved consistency by interpreting the axioms in the theory of the reals. But for the reals and the natural numbers, this method could not be applied. So starting with Hilbert 1904, he developed his Beweis theory, a proof theory. The logical apparatus, as well as the mathematical subject matter, had to be formalized. Formal proofs are then finite objects. Metamathematics is the study of these objects. And here Hilbert accepted Kronecker's restrictions to finitistic methods. Operations on formal proofs, such as reduction to a normal form, are to be, in an intuitive sense of the word, recursive. Relations between parts of proofs are to be decidable. the prime method of metamathematical proof is induction on the construction of formal proofs. Okay, so Hilbert's motivations, they're again epistemological, but they're a little bit different from Frege's. So for Frege, the axioms and the rules of inference were taken to be okay. And the key point was to show that, to make sure that, you know, some theorem follows from the axioms by the rules without any gaps. But by the time we get to Hilbert, he's not prepared to take the axioms as okay. In fact, he wants to prove that the axioms are consistent, and he wants to prove this in a bit of maths that he does regard as okay, finitary mathematics. And he does it by sort of proving that the idea is to sort of show that you can't prove from the axioms a contradiction. And so the idea of proving something from the axioms there has to be a sort of idea that you can show things about in finitary mathematics. And so again, the sort of upshot of that is that claims such as, for example, you know, this array of symbols is a proof of that claim are going to be decidable. Okay, so the third example I'm going to give from the history is just is Gödel. So this idea, well, here's a quote from Gödel: "The concept of formal system, whose essence it is that reasoning is completely replaced by mechanical operations on formulas." And then he said, "For any formal system, provability is a predicate of the form. There is an X such that X be Y, where B is primitive recursive, and hence, as he says a little on a different page, decidable." So this sort of decidability of this relation, X is a proof of Y, is you know, crucial to Gödel's first incompleteness theorem, you know, which is one of the most central results of formal logic as we know it. Okay, so the idea there is, okay, so this idea that proof checking there should be an effective procedure for proof checking, or decision procedure, is, I think, you know, really is part of the core conception of proof in formal logic. And so then the question is whether we should add something to this. And this proposed addition is from more recent literature on proof complexity. And the addition is that, so core to the idea of a formal proof is that we have this decision procedure that, given a proof candidate and a claim, will tell you, yes, this really is a proof of that claim, or no, it's not. And the proposed addition is that this procedure should be what complexity theorists call feasible, or more precisely, it should be a polynomial time procedure. So that is, the running time of this procedure that checks a proof should be bounded by some polynomial function of the length of the thing being checked, the proof. So that's sort of important to, just like I was saying before, this proof checking procedure, to understand what I'm talking about, it's important that it's not a proof constructing procedure, it's a proof checking procedure. And so when we talk about it here being polynomial, it means in the length of the proof, not the length of the formula being proved. So that's the proposed addition that comes from this more recent literature starting in the 1970s. So I'll give you some quotes. So Urquhart, the literature of mathematical logic contains a very wide variety of proof systems. We need a general definition of a proof system. Okay, well, I certainly agree with that bit. That's what this talk is about. What is the general definition of a proof system? And then he goes on, the crucial property of a proof system is that, given an alleged proof, there is a feasible method for checking whether or not it really is a proof, and if so, of what it is a proof. Okay, and in that context, what he means by feasible is polynomial. So this is this thing sort of in pretty standard in complex computational complexity theory, the Cobham-Edmonds thesis that feasible is sort of taken to mean polynomial. Anyway, that's the sense in which he's using feasible here. The next quote is a little bit more explicit. So he actually uses the word polynomial. So next quote: "One can consider many different formalizations, and it is difficult to find a classification schema which would cover all. Okay, so again, that's the project of this talk. Like we've got many different particular formal proof systems. But what we want to talk about is go up a level and sort of cover them all in some general idea of what is a formal proof. Okay, so it goes on. There is, however, one basic property which all formalizations of the concept of a proof must satisfy. It must be computable in polynomial time, whether a given sequence is a proof of a given formula. Okay, so the original core conception was it must be computable whether the given sequence is a proof of the formula, but now he's saying that the basic property is that it must be computable in polynomial time. Okay, a couple more quotes. What exactly is a propositional proof? Cook and Reckhow were possibly the first to make this and related questions precise. Okay, so that's referring to where that Cook and Reckhow in the 1979 paper is the origin of this idea that I'm now considering this addition that the proof checking procedure must be polynomial. Okay, quote goes on. We identify a proof system with a polynomial time procedure that checks the correctness of proofs. Okay, final quote. 3 properties that seem necessary for any method of certifying tautologies. Every tautology has a proof. Only tautologies have proofs. So that's completeness and soundness of the proof system. And then the one that I'm interested in is this last one. And valid proofs are computationally easy to verify. So again, this easy is another word like feasible that complexity theorists use as a kind of shorthand for polynomials. Okay, so that's the proposal. And what I want to do now is consider is this really part of the very idea of a formal proof? Should we take that to be a sort of extra necessary condition on being a formal proof, that the proof checking procedure be polynomial, not merely computable or effective? So I'm going to go through 4 arguments for this view and sort of reject them all, and then the conclusion will be no, we shouldn't add this thing. So, and the arguments are sort of, some of them are from the literature, but some of them are kind of one of them I completely made up, and one of them I've sort of extracted from the literature. But anyway, we'll see them as we go on. Okay, so the first one is what I'm going to call the argument from convenience. So if you take a kind of central result, example of a central result from this proof complexity literature, from the original Cook and Reckhow paper that I mentioned, here's the result. There's a proof system in which every tautology has a short proof if and only if NP equals co-NP. And by short proof, they mean one whose length is polynomially bounded. Now, so the point to note here is that result wouldn't be true if it wasn't part of the meaning of proof system there, that the proof checking procedure is polynomial, then that theorem as stated would not be true. So the first argument is kind of, well, look, it's just convenient in this literature, instead of every time we want to state a result like that, we have to add these words, there is a polynomially checkable proof system in which every tautology has a short proof, if and only if NP equals co-NP. We just say, look, by proof system, we're going to mean polynomially checkable proof system. Now, I think that's fine. If that's what's going on, then that's completely fine. But then it isn't actually a proposal for adding something to the core idea of a formal proof. It's just a proposal to, it's going to be convenient in this literature. If we use the term this way, it's going to save ink or whatever. So I've got no problem with it if that's all that's going on. But then it just isn't a proposal to add something to the very idea of a formal proof. But actually, that's not the way. So that's the first argument. It's kind of harmless but irrelevant to my concern. But actually, it's not. It's not the way people actually talk in the proof complexity literature, and that sort of brings us to the second argument. So the second argument is I'm calling the argument for intuition, and this is the idea that it's just kind of intuitively obvious that the proof checking procedure has to be polynomial. And So, I mean, here's a sort of like Urquhart, he talks about, the crucial property of a proof system. He doesn't explain why it's crucial. So I guess one natural interpretation of that is it's just meant to be intuitively obvious. And the next quote, a basic property which all formalizations must satisfy, and then later refers to this as a trivial observation. So again, the natural interpretation of that is it's just kind of intuitively obvious. Again, in this other paper, Segerland, he talks about properties that seem necessary for any method of certifying tautologies. Okay, so that's the second argument. It's just intuitively obvious when we think about it that this proof checking procedure should not really be computable. It should be feasibly computable or polynomial time. Okay, so my response to that is to sort of exhibit some examples of proofs from the literature that don't fit this intuition. Okay, so if we go to Hughes and Creswell, a new introduction to modal logic, they introduced this proof system K, proof system for the modal logic K. Well, in fact, they call the proof system K. And one of the axiom schemas is this thing PC. If alpha is a valid formula of PC, then alpha is an axiom. And then they present proofs like this one. And I don't know if you can see this pointer when I move it, but like there are these lines like PC1, PC2, PC3 that are instances of that axiom schema. So the idea is that this PC1 is a tautology of propositional logic. And now if you think about checking this proof, how would you check that that was legitimate formal proof? Well, when you go to line 1, you'd have to check that that really is a tautology of propositional logic, and similarly on line 6 and so on. There's no known polynomial time procedure for taking a formula and checking whether it's a tautology. In fact, most people in the area think there can't be one, because if there were, if there were, then P would equal NP. And because most people think that P does not equal NP, they also think there can't be a polynomial time procedure for taking a formula and checking whether it's a tautology. And Hughes and Creswell they're very close to being explicit that this is fine. It certainly doesn't seem to be something that they just sort of overlook. Like they say in this footnote, the fact that the axiom schema PC gives us infinitely many axioms does not conflict with our requirements for a satisfactory set of axioms, since we have in the truth table method, for example, an effective way of determining whether any given formula is a valid formula of PC or not. Okay, so it's sort of natural to conclude from this, if I go back to the previous slide, that the thought is like, well, look, when you get to this line 1 and you want to check, is this a legitimate proof? You can do a truth table to see whether line 1 is a tautology. But that procedure, doing a truth table, is exponential. So it's pretty much explicit here that the proof checking procedure does not need to be polynomial. And sort of for those who were here for Rob's talk, in the previous talk, he actually did the same thing. He took his axioms for this system of temporal logic, all tautologies. And another place where you see this is in John Burgess's book about philosophical logic, where again he does this system of temporal logic and lets alpha, any tautology alpha is an axiom. And he even does another thing goes a little bit further and has this rule of inference, the rule of tautological consequence. So if you look up here, you're allowed to infer B from A1 through AN if B is a sort of, follows logically from A1 through AN in propositional logic. So if you look through this example that he gives of a proof, when you get to this line 3, you've got to check that 3 really does follow from 1 and 2, in propositional logic. And again, that's not something for which we have any polynomial time procedure, and if P is not equal to NP, then there is no such procedure. Okay, so that's my response to that argument. Is to exhibit these examples of formal proofs from the literature that do not meet the requirement. And you can sort of take it in two ways. You can take this as a kind of argument from authority, or you can just take it as a sort of appeal to your own intuition. You look at these things and you agree, yeah, these are fine as formal proofs. So, and note that I just went back a few slides. Hughes and Creswell actually say here, we shall first prove two theorems, in full detail. So they don't take these things to be kind of abbreviations that can be filled out into formal proofs. They take them to actually be formal proofs as they stand. Okay, so that's the response to the argument from intuition. Well, look, it's not intuitively obvious, because if it was, then nobody would, when people read this book of Hughes and Creswell, they would have said, hang on a sec, there's clearly something wrong with this, which people don't. Okay, so the third argument. So here's a quote of a bit more from this paper that I quoted earlier. And it says, since there are only finitely many truth assignments to check, why not allow the statement itself as a proof? So, take a formula of propositional logic. Just write that down and say it's a proof of itself. Why can't we do that? There's an effective procedure for checking whether or not it's a proof of itself. For example, do a truth table. So according to the core conception of a proof, that should be fine. But they say, why not allow this? The assumption seems to be that we shouldn't allow this. And so then they say, what extra value is there in a filled out truth table or a derivation using some axiom and inference scheme? And they say the key observation is that a proof is easy to check, unlike the statement itself. So I don't exactly know what the intention behind this paragraph was, but I think you can extract an argument from it. And that's the argument I want to consider now. So the argument is, we should not, intuitively, a formula of propositional logic all by itself should not be allowed to count as its own proof. And how are we going to rule that out? Well, we're going to say that the proof checking procedure has to be not merely an effective procedure, but it has to be polynomial. So let's consider that argument. So now I want to say why that's a bad argument. And basically the reason why it's a bad argument is that it doesn't, even adding this extra requirement on formal proofs does not rule out formulas being proofs of themselves. So let me just explain that for the next few minutes. So I want to introduce a certain kind of formula of propositional logic. So it's not essential for this purpose, but it's kind of easier if we just think of the sort of basic propositions of the language as being written as P sub 1, P sub 2, P sub 3. And then what I call a conjunction of distinguished literals, or CDL, is going to be a conjunction of one or more literals, so either a basic proposition or a negation of a basic proposition, in which no basic proposition occurs more than once. So, for example, not something like P1 and not P1, or P1 and P1 and P2. Not like that. It just, you can't have a repeat of the basic proposition, of any basic proposition. So there's some examples of these conjunctions of distinguished literals. And then if you can, I'll refer to, or I'll call the signature of one of these things, the sequence of positive integers, comprising the subscripts on the basic propositions in the order in which they occur in that CDL. So for these examples here, these are their signatures down here. So it's just like 2 followed by 4 is the signature of that CDL. And then also 2 CDLs are cosigned if they have the same signature. Okay, and then the final the thing that I actually wanted to define is this notion of a cosigned disjunctive normal form. So what that is a disjunction of 0 or more of these CDLs, but they're all cosigned. So it's a disjunction of 0 or more cosigned CDLs. So this is 275 is its signature, 275 is its signature, and so on. So a disjunction of ones that have the same signature. And we use this bottom symbol for the disjunction of 0 of these things, and just stipulate that it's false on every interpretation. Okay, and so to get a sort of intuition for what these things are like, have a look at this table. So here is just this is just an arbitrary formula of propositional logic, just as an example. So you stick in here any formula you like of the language of propositional logic, and then here's its truth table. And then you look at the rows on which it's true, and you write down for each of those rows, you write down a sort of description of that row, and then you disjoin them. So the first row is P3 and P1 and P4, they're all true. So that's described there. This third row on which it's true, P3 is false, P1 is false, P4 is true. So, not P3 and not P1 and P4 is that one. So you describe each row and then you disjoin them, and the result will be one of these cosine disjunctive normal forms. So that should give you a feel for what these kinds of formulas are like. And also it actually illustrates that every formula of propositional logic is equivalent to one of them, because this thing over here is going to have the same truth table, because the first disjunct is true on the row that it describes, and it's false on all the other rows. And the second disjunct is true on the row that it describes, namely that one, and false on all the others, and so on. Okay, so the thing about these formulas is each of those can be regarded as a proof of itself. So, or more precisely, if you take a formula, one of those CDNFs, then it's kind of simultaneously a proof candidate of 3 different claims: the claim that it itself is unsatisfiable, the claim that it itself is satisfiable, and the claim that it itself is a tautology. So it's a proof candidate of all 3 claims. And then which of those claims is it actually a correct proof of? Well, any of them for which it passes the proof checking test that I'm about to lay out. And the key point to note about this test is it is feasible. It's polynomial time. Okay, so here's the test. So you take this formula in CDNF, and the first part of the test is you say, well, look, is it the bottom, that particular disjunction of 0 CDLs? If it is, then it's unsatisfiable. We said that that's false on every model. And if it isn't, then it's satisfiable. So all you have to do is just look at the formula. Is it the bottom? No. Well, then it's satisfiable. Why is that? Well, because if it's got even one, like if you go back to the previous slide, if there's even one of these things there, then there's going to be a row on which it's true, namely the one described by that disjunct. Okay, so that tells us whether it's satisfiable or unsatisfiable. And then if it is satisfiable, then the second part of the test will tell us whether or not it's a tautology. And so the second part of the test is look at the first disjunct of the formula and count the number of basic propositions in it and call that n. And then look across the whole formula and count the total number of disjuncts. So if we go back to the previous slide, here, for this example here, n is 3, because there's 3 basic propositions in the first disjunct, and m is 4, because there's 4 disjuncts. So you count those 2 numbers, And then you take the second one, M, and you see whether or not you can halve it, and then halve it again, and halve it again, and so on, in times. Or like either you can do that, or you're going to run out of, like, so, in this case, suppose we have M is 4. So if you think of it, you can think of it as a kind of Turing machine. It's got like 4, it's got like 3 strokes representing the number of basic propositions in the first disjunct, and then 4 strokes representing the number of disjuncts. And then you can sort of think of it as go along and, like, erase one of the first block and then go to the second block and erase half of them. And then come back to the first block, erase one more, erase half the second block, and just keep doing that. And either you'll end up, there aren't enough left in the second block to keep doing it. So that's what had happened in this case. You've got 3. You've got 4 in the second block. So you can halve it once and you'll get 2. You can halve it again and you'll get 1. And then you can't halve it anymore. So you couldn't halve it 3 times. Okay, so that's what's going on here. So suppose you can halve it 3 times. Well, what that means is that M is 2 to the power n. And in that case, we will say, yes, this formula is a correct proof that it itself is a tautology. And what's going on there is, well, look, like suppose it's got 3, suppose it's got, for the sake of example, 3 basic propositions in the first disjunct. Then there are only 2 to the power 3 ways of assigning truth values to those things. And a tautology is something that's true on all of them. And each disjunct represents exactly one of them. So for it to be a tautology, there have to be 8 disjuncts. That's the idea here. So tautology is just true on every row, i.e. it has one disjunct corresponding to every row, or every assignment of truth values to the 3 basic propositions. There's 2 to the n of those. So if there aren't that many disjuncts, then it's not a tautology. Okay, so that proof checking procedure is polynomial. So here's the thought that, like, suppose you thought you thought intuitively a formula can't be a proof of itself. So you introduce this extra polynomial checkability requirement to rule that out. Well, the point of this argument is, well, look, it didn't work because you've still got all these formulas being proofs of themselves. And you could, even if you want, like, consider a language in which only these things count as well-formed formulas. Then in that language, every formula would be a proof of itself. So you kind of have a language where the proof system just was the formulas themselves. There was no kind of separate proof system. Okay, so that's the response to the second argument. And then I guess oh yeah, I can go through this. I think I've got enough time. So you can, so far I've just talked about single formulas, but you can sort of extend this very easily to talking about sets of formulas and arguments. So I talked about before the signature of a CDL. You can now talk, and then one of these cosine disjunctive normal forms, all the disjuncts have to have the same signature. So we can now just talk about the signature of the CDNF itself. And then you can call a set of these formulas cosine. All the formulas in it have the same signature. And again, you can view a set of cosine CDNFs as a proof of its own satisfiability, or of its own unsatisfiability, as the case may be. And to check whether this set of formulas proves its own satisfiability, you just look through and see, is there a disjunct that appears in every one of the formulas? It's just basically, it's just the same as saying, is there a truth table row in which they're all true, because the disjuncts just exactly describe truth table rows. If there isn't, then the set's unsatisfiable. Okay, and similarly for arguments, if you take an argument where the premises and the conclusion are all have the same signature, then you can take that argument to be a proof of its own validity or its own invalidity, as the case may be. To check it, you just say, well, look, is there some disjunct that appears in all the premises and does not appear in the conclusion? If so, it's a proof of its own invalidity. And if there is, then it's the proof of its, sorry. If there is a disjunct that appears in every premise and not the conclusion, then the argument is a proof of its own invalidity. And if there isn't, then it's a proof of its own validity. Okay, so that's the third argument. So the fourth argument is, this is not one that this is just one I made up. I didn't find this in the literature, but so here's the argument. Proof is fundamentally an epistemological notion. Now, I think that's true. I agree with that. And so that's actually the way I've presented this. It looks like it's got two premises and a conclusion, but really that's just a kind of preamble that proof is fundamentally an epistemological notion. Then there's one premise and one conclusion. So the premise is something like, look, you don't know some theorem until you have checked the proof of it. So suppose someone just gives you a proof of some theorem. You don't immediately come to know that theorem. That's the thought. You have to actually check the proof. And then once you've sort of checked through it and seen that it's a correct proof, then you can be said to know the theorem. That's the premise. I think that's, I'm totally prepared to grant that for purposes of argument. I think that's pretty plausible. But then the conclusion is supposed to be, well, look, in that case, the checking procedure must be feasible. So the thought is, well, look, to know the theorem, you have to check through the proof. So if you're ever going to know any theorems, it has to actually be feasible to check the proofs, or you couldn't know any theorem. So that's the argument. Now, I think I guess there's two things one can say about this. So the first one is just as a sort of preliminary point. I think you can sort of see that this can't be a good argument because it proves too much. So first I'll explain that, and then I'll sort of try and explain exactly what's wrong with the argument. So the proves too much point is, suppose we grant what's just been said. You can't know the theorem until you check through the proof. Well, in that case, for you to know a theorem, you don't have to construct the proof. You just have to have a proof and check it. But still, the proof has to have come from somewhere. So generally speaking, nobody's going to know any theorems unless there are proofs that have come from somewhere. So it's sort of, it would, by the same reasoning, it would have to be the case that, look, for you to know a theorem, somebody has to be able to construct it in order for it to be there for you to check. So in order for any of us to know any theorems, someone has to be able to construct the proof of the theorem. Therefore, conclusion by a kind of parallel argument, the proof construction method must be feasible. Now that pretty clearly proves too much, because as it stands right now, we don't have any feasible, that is, polynomial procedures for constructing proofs of tautologies of propositional logic. And most people think we can't have any, but we clearly do know some theorems of propositional logic. So there's something wrong with this kind of argument, because you can just do a little variant of it that clearly proves too much. Not only that proof checking has to be feasible, but that proof construction has to be feasible or polynomial. So what is wrong with it? Well, I think that exactly what goes wrong with this is that it sort of trades on two different meanings of the term feasible. So one is the sort of technical meaning in complexity theory, which is polynomial time. And the other one is just some sort of ordinary intuitive notion of whether or not you can do something. And I don't think they're the same. They're not exactly the same notion. And so a conclusion that, so if you take that premise, you don't know the theorem until you've checked the proof. Something that clearly follows from that is, for you to be able to know the theorem, you have to be able to check the proof. You know, it has to be the case that you can check the proof. So in this ordinary sense, it has to be feasible. But I'm just going to stop using the term feasible, because I think it actually is. It's using that term that makes this argument look convincing when really it's not a good argument. So, well, it's kind of using it in two senses. So just forget the term feasible now. So, okay, so for you to get to know this theorem, you have to be able to check the proof. I think that's right. But let's call a polynomial time algorithm now a not a feasible one, but an efficient algorithm to make things a bit clearer. So it doesn't follow that for you to be able to know the theorem, you have to have an efficient procedure for checking the proof. That it does follow that you have to be able to check the proof in this ordinary sense, but it doesn't follow that you have to have an efficient procedure. So these are sort of claims on two different levels. So whether or not you're able to check the proof is really just a matter of kind of the sheer size of the proof. Whether or not you have an efficient procedure is about how the sort of running time of that procedure scales as the input to the procedure increases. Whereas the can you do it, are you able to do it, is really just about the sheer size of this one particular task, not of the sort of scaling of how hard the task gets as the input gets bigger. Or sorry, how long the task takes as the input gets longer. So there's plenty of things that we, can do in that intuitive sense for which we have no efficient procedure. And also conversely, there are things that we have an efficient procedure for doing them, but we still can't do them. So, if you just consider truth tables, then when you, ask intro logic students to make some truth table with, 4 or 5 for some formula that has 4 or 5 basic propositions in it, they can do that, but they don't have an efficient procedure for doing it. And, conversely, if I gave you some, 30,000 page thing, what happened? Oh yeah, if I give you some 30,000 page thing, which is about the size of the Encyclopedia Britannica, and some formula propositional logic with just 20 propositional letters in it, and I say, can you check that this is a correct truth table for that formula, then you have an efficient procedure for doing that, but you can't do it. You just don't have time. Okay, so these are different notions, and so I think all it actually, so I take this premise, you don't know the theorem until you've checked the proof. Let's grant that, but it doesn't follow from that there has to be an efficient proof checking procedure. All that follows is that in order for you to know this theorem, you have to actually be able to check this proof of it, or some proof of it. Okay, so that's the 4 arguments. I don't think there is any good argument for adding this feasibility requirement to the sort of very idea of what constitutes a formal proof. So I think we should just stick with the core conception. Okay, so that's it.